All right. I'll begin with a word of prayer. I'm starting here. Heavenly Father, we thank you for this day. Again, I thank you for the students. Just ask that you'd guide our steps today and encourage them to continue working on the course and just do their best, Lord, each day. Lord, in your name I pray, Lord Jesus. Amen. All right, so you put this nonsense away. Let's see here. So we are now into differential equations. So I would, remind you, if you didn't know already, that I follow these, articles. I've called them articles. They're basically chapters in a book I haven't quite published or anything. But these are my calculus notes, all right? So the next thing we're covering is differential equations. So, and just introduction to differential equations, all right? So in here, what we're going to do is we're going to look at first order differential equations. And so the first order of business is to define, like, what is a differential equation and what are our goals and purposes here, all right? So let's get to it. And I need the projector for a little bit because, well, first of all, there's really not much to write down here just yet. So I'll just read through some things, and the things that are very important I will write again once we get past this, okay? But to start with, first order differential equation, you can write it as dy dx equals to some function of x and y, all right? A solution, an explicit solution, is a function that you can plug into the differential equation and it makes it true. That's called an explicit solution, all right? So, for example, if you have dy dx equals to x squared, then you notice that, well, you could integrate both sides here, and then you get y is equal to 1/3 x cubed plus a constant, right? So there you go. So we just solved that differential equation by direct integration, right? So actually, search your heart and realize that you've already been solving differential equations. The full first quarter of this course has been just solving differential equations of the form dy dx equals to the integrand. Every integral you do, you're solving a differential equation, right? Integrate, e to the x dx. What are you doing? You're finding y such that dy dx equals to e to the x, Every integral is a differential equation, actually. So, but not every differential equation can be solved by integration, unfortunately. Not like that, anyway. Like these ones, y prime prime plus ty squared, y equal to 0, or y prime prime plus y cubed equal to 0. You can't just integrate those, because in order to integrate those, you'd need to know the answer. Like to solve for y, to integrate to find y, you'd have to integrate y over here. But if you don't know y, then how are you going to... That's the problem. I mean, you can't just integrate. The difference here was, you have dy dx equals to x squared. So all of the thing you're trying to find, y, is isolated in the derivative. In contrast, in these differential equations, you've got y both places. So anyway. All right, so a little bit more terminology just to get this on the table here. It's called a first order differential equation if the highest derivative is like the first derivative. This would be a second order differential equation because it's got a y prime prime. Yeah. This one is, you might think it's third order. It's not, because it's still second order, because the highest order of the derivative defines the order of the differential equation, all right? Linear differential equations are the nicest ones. They're ones which the derivative and the dependent variable both appear linearly, all right? This here is still a linear differential equation despite the fact there's a t squared, because it's the y prime prime and the y appear linearly. So this is still a linear differential equation. So the linearity speaks to the dependent variable. That one I had in the previous slide was nonlinear because of the y cubed. Let's see here. We can also talk about systems of differential equations like this. dx dt equals to x plus y, dy dt equals to minus x plus y. That kind of thing might come up in the study of, say, like a predator-prey problem. Maybe you've got tigers and bunnies on some island, and the bunnies are eating the tigers, right? And then, oh, wait a minute, no. Other way. And then you can talk about their birth rate and death rate and couple them and study. This is a predator-prey problem. Newton's law. Some of you are taking physics right now. Newton's law is a differential equation because you're solving ma equals to m, well, that's d squared r dt squared. In 3 dimensions, this is actually x prime prime comma y prime prime comma z prime prime. So you're actually solving a system of 3 second-order differential equations. You didn't know you were that sophisticated, but that's what you just did, right? We have ways around this, though, don't we? Like, we hide this mathematics, don't we? Is differential equations a prerequisite for Physics 231? It is not, right? Not even Calculus 3. For shame. No, for reasons of retention of engineering students and history. But anyway, differential equations are everywhere, is my point to you. At the base of every physical law is a differential equation, right? So understanding how to solve differential equations is really part and parcel of understanding the basic language of physics as we understand it today, all right? So the first chapter in that story is to understand how to solve first-order differential equations, all right? And that's what we're gonna get into here. So here's a more complete definition. See, because we don't always find an explicit solution. Sometimes we find what's called an implicit solution. Implicit means that you've got some function, some equation that wraps x and y together, right? Like the equation of a circle, for example, x squared plus y squared equals to 1. That implicitly defines y as a function of x. Not everywhere, right? Y is, you guys wanted a pre-calculus review, right? So this is a circle. Why is y not a function of x? Vertical line test, right? But nevertheless, x squared plus y squared does implicitly define y as a function of x for a circle, which means locally you can solve for y as a function of x, right? So here we'd have what y equals to the square root of 1 minus x squared, right? Down here, what would we have? Negative, right? And is there any place where I cannot solve for y as a function of x? Here and here. There you cannot solve for y as a function of x. Not locally anyway, if you want it to be defined above and below the point, yeah? That's the thing, is you're stuck. If you do any interval of x around here, you necessarily fail the vertical line test, because no matter how far you shrink it, you're going to fail the vertical line test. So those 2 points are the 2 places where you cannot solve for y as a function of x on a circle, because you're at the place where the plus and the minus meet, which means you necessarily fail the vertical line test if you try to do it there. But usually, with the exception of ugly exceptional cases like that, if you have an equation involving x and y, you can write y as a function of x, at least locally, all right? So that's your pre-calculus review. Yes?
Would it not be root 1 minus x squared because if x is 1 in that case?
But then that doesn't define all the solutions to the circle equation local to that point, because there's also the minus solutions equally close. You can't, I mean, you're just ad hoc chopping this piece off, you know? But if you're going to say, I want to find the totality of the curve defined by the circle close to this point as a function of x, you can't do it, because there's also that part that sweeps down there. Now, listen, the full explanation of these things really is not even given in Calculus 3. The itch we're scratching at the moment is actually what's known as advanced calculus. So I cover these things more carefully in like the Math 332 course here when we offer it. Okay, so anyway, listen, we don't need all that. The bottom line is, it's simply this. If you can write y equals to formula, you've got an explicit solution, all right? If you have the equation involving y and you can't necessarily solve for y, that's an implicit solution. A lot of times we can only find implicit solutions, and that's okay. This is probably, rather than talking about it, let me, here's an example, right? dy dx, where's my laser? So here's dy dx equals to x squared. I say this has general solution x cubed over 3 plus a constant. What I mean by that is that any differential equation, any solution to this differential equation falls under this formula. Right? That gets you everything. And if you have an initial condition, like you want the point x naught y naught to be on the curve, then you can find a value for c to make it so, you know. you can put 1 comma 4/3 to be a point on the solution curve, and then that gives us 4/3 is 1/3 plus c, right? And then we solve for c, we get c equals to 1. So therefore y equals x cubed plus 3. X cubed over 3 plus 1 is the solution to this initial value problem. This differential equation, and that point has to be on the curve. Now, confession, I have not explained how it is. Oh, yes, I did. Well, I think I did in the last page, didn't I? You can see how to solve this, right? You just integrate. Okay, so this kind we can do, I should admit. But, so I said, in retrospect, every integral we've solved so far has been of the form, well, basically we've got this integral, right? This is the problem we're facing. And what is this equivalent to? It's equivalent to the problem dy dx equals to f, right? So yet again, like I was saying, we've been solving differential equations all along so far. But we will soon learn that that is not enough. There are many differential equations which will need another method. So there are 3 methods we'll learn in here. Separation of variables. Separation of variables is very, very simple. It's very simple. Very simple. I've done that in physics if you're taking my physics class. The actual separation of variables part was easy. The calculus 2 integral I did after that was not easy. But it doesn't have to be hard. Separation of variables can be easy. Integrating factor method requires more attention to detail, and you have to learn a method. So this is not intuitive. I wouldn't say that integrating factor method is intuitive. There's a dirty trick involved here. I'll show you. All right. And substitution, well, that's where the creative edge is. So there's a lot of different things going on in there. So, like I said, it's all right. So the real reason I have this out was not for all that. It's for this. So visualizations in Euler's method. So if you have a differential equation like dy dx, we can visualize that. Like, what are we trying to do? We're trying to find this one, right? Dy dx equals to y. What does this mean? You're looking for curves whose value is equal to their derivative, right? And so you can plot that, if you like. So here I've searched the internet, and at the moment this is what I found. And the annoying thing is, you know, I do this search periodically, and inevitably some of the internet tools, people die or get fired, or, you know, copyright stuff, you know, Java sunsets, whatever, who knows? It's endless and annoying, the sunsetting of technology. But this is currently working, I think. And if you click on that link right there, it'll take you to here. And so like here, what you're looking at, it's kind of hard to see, but that's, I think, y prime. Maybe he's got r prime. Anyway, basically this just means dy dx equals to y is the long and short of, oh, here it is, dy dx equals to y. What these little dashes are just like, imagine you had a tangent line, right? What would the slope be? Well, the slope is given by y, right? Dy dx equals to y. That means horizontal here, right? Positive slope up here, and it's the same positive slope, right? Slope 1, slope 1, slope 1, slope 1, slope 1, slope 1. You get the idea. Slope 2, 2, 2, 2, 2. Slope 3, 3, 3, 3, 4, 4, 4, 4. Slope 5, right? Down here, negative slope. Negative slope 1, negative slope 2, negative slope 3. And so this is kind of like a grown-up version of connect the dots. But instead of connecting the dots, you're connecting the slopes, right? So your goal in drawing a solution curve is that your curve has to be such that it's always tangent to the little tangent lines as it crosses, right? So like here, this is slope 2. It's got slope 3 up here. It's got slope 4 up here. It's got slope 5 up here. Do you get the idea? All right. This would have taken me 20 minutes to draw on the whiteboard. so technology has its place. Now, if you're looking at the electronic version of the notes, you could actually click this link. And yeah, I'll allow it. It'll take you to here, and you can actually play with it yourself, you know? So like we could put in, I don't know, y squared, see what happens. And you could actually click on it. Come on, you can click on it. Oh, you can't click on it. Oh, this is worthless. Garbage. Oh, okay. So he lets you put 4 plots. Oh, 4. You can put 4. You can put 4 solution curves, and that's probably adjustable. This is all done through something. Ooh, there's the zoom feature. This is all done through something called GeoGebra, which is, you know, free, open source software. you can make beautiful plots in this GeoGebra stuff, all right? Dr. Wang used to be a big fan of it. Now, if you are around Dr. Wang, he only speaks of Julia. It's the only, his heart only is for Julia. In terms of computer software, he is married. But let's see here. So let me get back. All right, so that's okay. This is what's called an isocline plot. Isocline plots are ones where you don't have arrows. It's just little dashes indicating the slopes, all right? I have better tools for, come on. Ah, yowzers. Okay, so, I'll go through the details here after I put this away, okay? I'll come back to this example, work through it. But long story short, dy dx equals to minus y over x over y has solutions of circles, all right? So you know what circles look like, right? So when we go and use this slope, this plotter, this isocline plotter, what we should see is circles, right? But what happens? Let's see. See this? This is what happens, right? So if we understand enough about mathematics to know we're looking for circles, this is the kind of thing you should do with software, right? You guys will be in jobs where you have to use software. And you should never trust software, right? Because some of you know software engineers, and so you know the kind of people who wrote the software for you. Sorry. Some of you are probably software engineers. But I'm just kidding. Probably. But as you can see, I mean, it's not their fault. They tried to plot. They got half of it right. It's all nice and pretty up here. There's your circles, and then what happened? Advanced calculus happened to them, right? This is those places where we can't write the function as the solution as a function of x. And so when you try to code that, if you're not aware of that issue, this kind of stuff happens to you, right? That's not true. That's not what the solutions actually look like, right? I mean, up here it's okay, but you know, so one of the things we're after here, and just as more generally true in mathematics, is giving you a situational awareness so that you can sort of test case software and make sure that it's not lying to you, right? Yes, eventually in your job we don't want you to solve integrals by hand, but we also want you to know enough that you know when the computer's lying to you, right? And that's a skill that takes some time to acquire. That's what we're after in here.
They did get the slope lines right,
though. They did get the isoclines are right. Now, so here's a trick that we're going to use. We can take, all right, check this out. So we can take dy dx, and we can reimage it as, rather than dy dx, we can look at it as dy dt over dx dt. We're introducing a parameter t. In other words, we can write y as a function of time, and we can write x as a function of time. And in so doing, you can trade dy dx for, like, a over b, where a is the top and b is the bottom. In other words, you can trade dy dx for this corresponding system, dy dt and dx. Aw, man. Really? Dude. What's that? No, what's this? That's x, right? That should be x. I mean, this matches that matches that, all right? And the reason I want to do that is because, okay, so at the end of the course, sorry, this is just, so right now what's happening is an argument for this material being moved to the end of the course, because in order to fully explain to you what I'm about to do, I need to tell you a little bit about parametric equations. What are parametric equations? Going back to this example again, how can you describe the whole circle as one parametrized curve? Introduced parameter, what is the parameter used? T, right? All I got to do is write this. X equals cosine t. Good grief, I can't spell. Cosine t, and y equals to sine t. These are called parametric equations, all right? In physics, I will always do like this. R of t equals to cosine t sine t. The reason I do that is because the cosine and sine, they're not really much as equations as they are mapping, okay? I mean, that's the truth. It's a mapping. You're mapping the real line and you're gluing it around a circle over and over and over again. In this approach, there's no difference between all of the points above and below the equatorial points. They're all treated equal. This is equitably treats all points on the circle as if they're the same. So in this approach, this way of packaging mathematics, you don't suffer like coordinate defects at like where y is equal to 0, where you've got, that thing. So anyway, long story short, if you have software which is built on this parametric approach, it doesn't get these ugly things, all right? And so I will post this, I will try to post this in Canvas if they don't prevent me.
Professor,
Yeah.
the parametric equations are cosine with respect to t, just substituting it as x and y.
Well, yeah, what makes it a parameterization of this curve is that if you take these and you plug them into the equation, it works. So like more generically speaking, and since you asked, otherwise I wouldn't say this, but if you have equation f of x comma y equals to 1, so this is an equation. This defines, x as a function of y implicitly. What's a parameterization of this equation? It is two functions, one for x, one for y, such that f of, let's say, I'll use phi for the sake of being weird. Oh, gracious. I guess I'll just write x of t. I don't know if this makes sense to you or not, but so x of t and y of t are functions that when you plug them in, you get 1. That's, if you can write x as a function of t and y as a function of t such that it solves the same equation, then that's a parameterization of the curve. So like cosine and sine are a parameterization of that curve. I have asked you no homework about this whatsoever until much later in the course, yeah.
So is the parameterization, is that graph ever? Or
Can you graph a parameterization? Of course, yes. And
is that the circle that I'm asking?
here's how you graph a parameterization. If I can't, is that the circle? I don't quite understand your question. Say again. Just repeat your question. I need to.
So the x equals cos t and y equals sine t, like is that like a new equation for the circle?
It's a different way of approaching the circle. So the difference in viewpoints is do you want to define, how are you going to define a curve? Do you want to define a curve in terms of this being the solution set of an equation? This is what a graph is in some sense. Like y equals f of x, you're really looking for where y is equal to f of x, right? You could repackage that as y minus f of x equals to 0, right? Or the circle's more obvious, right? X squared plus y squared equals to 1. What's a point on the circle? Well, you got to find a point that you plug into that equation, it works, right? The parametric view is the opposite thing. It says you define the object by a mapping. It's the image of a mapping. So you plug in a point, and the mapping gives you back a point. Plug in another point, it gives you another point. So you're not solving an equation. Really, you're putting numbers in and mapping them. And that's what's going on here. I plug in a t, it gives me a point out. So this is a software that'll help you, desmos.com, free. And it's nice because it allows you to add sliders. So like what I'm looking at here is cosine t sine t, and it's been plotted from 0, the range of the parameter. Oh man, I really was not going to talk this much about parametric equations today, but you guys are asking me, so I'm doing it. All right, so 0 to a, like this. That is a plot. This is so you see what's happening. I mean, it's kind of hard to see, but circle, right? If I increase a, then we're plotting a little bit more, right? And let's see here. It won't make if I make 0 less than minus, if I make the range go from 0 to -1, that's bad math, right? So let me fix the slider here. We started at 0, and I'll let it go to let's say, come on, 6, and I'll let it go in steps of 0.001 just to make it take a little bit. And here we go. Let me make it bigger. So what's going on here is you're seeing how the circle is traced out as the time goes on, right? So this is literally, so I think of a parametric curve as a way of taking the real line and then using the parametric equations to define how you're laying it out in 2 dimensions, or you could do 3. Actually, this viewpoint's general. You could talk about a curve of matrices. What? Yeah?
Could you also think about maybe it's a three-dimensional graph of t and x and y looked on just on the 2 dimensions, like folded down into 2 dimensions?
Oh, I don't know. I just think about this 2-dimensionally in terms of the like I said, I plug in t equal to 0, it gives me 1, 0. I plug t equals to pi over 2, it gives me this point, 0, 1, and so forth. I mean, is this related to graphs in 3 dimensions? Sure. That's also true, but there are many things which are true. Sorry. Okay, so, sorry, I will stop chasing this rabbit. Let me get back to the, so all I was trying to tell you guys is that in terms of making pictures of differential equations, this is a way better tool. But these guys used to have a, well, anyway, so here we go. If we put in, so here's the one that comes default set to this. Let me show you what it looks like. And then the cool thing about this is I can just see I'm just clicking on here, and it plots the, whoa. That's called a stable spiral. Let's see here. So this is one of the packages which is available to you guys in MATLAB that you guys don't like. I've heard don't like, which is unfortunate because it's a very powerful tool. And the year I worked for the Navy, I kind of like did nothing but MATLAB the whole year. So
Sorry.
if you're sorry.
They use this to map
Funny.
gravitation of planets.
You could use it to do. You could study things like that. Let's see here. So let's suppose we have. What was the equation we had? I said the circle. The one that the other software did badly was what? I can't remember. It was. Oh, here. Let me work it out. Here we go. Example 1. dy dx. Excuse me. This one's kind of backwards. X squared plus y squared equals to 1. What differential equation is this a solution for? So I'm asking a backwards question to start with, just to confuse you guys. So my question is, what differential equation is this a solution for? And you could put an r squared over here. If I differentiate this, I get 2x plus 2y dy dx equal to 0. What I just did is called implicit differentiation, right? When do we do implicit differentiation? We do implicit differentiation when y is implicitly a function of x. And so solve for dy dx, and there you go. There's your differential equation. So I got minus x over y. So what I'm saying is, if you want to look at this thing using this MATLAB tool, this p-plane, the way to do it is to be a little bit sneaky and do dy dt equals to minus x and dx dt equals to y. And what I'm telling you is, if we do that, we'll get better pictures than we did with the GeoGebra isocline thing. So what did I say? X prime is what? I've already forgotten. Can you tell me? Negative x. And then the other one was it y?
Yep.
Okay. And let me make this window. I'm going to adjust the window so.
It's the other way around.
Other way around?
Yeah.
X is Y. Y.
X is y and y is x. All right. But still the plus and the minus, yeah?
No, plus and minus was
Oh, all right. All right. It actually wouldn't. You see, it wouldn't matter with the minus. See, because you could write that equation a different way, couldn't you? So this is what's called technically called the direction field plot, because instead of little just dashes, you have arrows, and that's because we're looking at the parametrized version. So the other thing about parametric curves, as opposed to just equations, is that parametric curves have a sense of direction. When I write these equations down, it makes the circle counterclockwise. And if you think about a circle, well, here's my question. Is the unit circle clockwise or counterclockwise? Assuming you know what a clock is. Counterclockwise is incorrect. I mean, the answer is, well, it's correct, but so is clockwise. I mean, a circle on its lonesome, x squared plus y squared equals to 1 is not oriented. You could go clockwise or you could go counterclockwise. And those have separate parametric equations. I think if you flip sine and cosine, that'll make it go the other way. But anyway, here it is. Check it out. Nice and pretty, right? No trouble at y equals to 0. See, because this approach the software is, it doesn't treat x and y as, it treats them on the same footing. So like, that's part of it. So anyway, so this is a good way to visualize differential equations. If you want to look at like, what do the solutions look like? So let's play this game. You guys make up any differential equation you want. dy dx equal to what? What do you want? So you guys make it up. So and I want to. I would. All right. All right. So secant cubed x, I guess, and then what? How about x squared minus 1? Sound good? I'm going to trade that for a 1 over cosine cubed x times x minus 1, x squared minus 1, because I don't want to find out whether or not p-plane supports secant. All right? So that's the kind of thing you need to... OK, so if we do that, what should we... I forgot. So OK, then we convert to... So this, I'm going to convert it to, I'm going to do y prime equal to 1, and I'm going to do x prime equal to cosine of x. I'll put parentheses around it. I'll caret it to the 3, and then I'll take that, put parentheses around that, and then multiply that times x, x squared minus 1. So you got to think a little bit about maybe the ASCII coding here. I'm not sure how much pre-processing their program does here. I said x prime was 1. Did I say that? No.
No, y prime is 1.
Y prime is 1. All right. I don't know why I don't know why I let you guys do this to me. All right. X squared minus 1 times parentheses cosine of x cubed. Was that it? So trust me when I tell you I cannot solve that differential equation. But if you want to know what solutions to it look like, here they are. Can you see how that might be useful in analyzing a problem? Yeah.
So we're going to be able to use that test.
You don't want me to give you a test where you need to use this. Definitely not. No. But I might ask you to do like the grown-up version of connect the dots on the test. I give you the thing, you trace out solutions. That becomes reasonable. Okay, so I've showed you the toys. Let me get back to the. Let me do some show and tell here. So we just went through. Come on. So I want to show you some of my, circles, one of my favorites, obviously. Here's another one. Yep.
So is solving differential equations just figuring out like where to put the...
Oh no, this is we haven't solved the differential equation yet. All we've done is visualize them. I will start solving them